All right, so if you have been kind of watching these mini lectures in order in terms of the influence that magnetic fields have on charged particles, in the last couple of mini lectures, it was 2 parts, you might have said to yourself, well, wait a second, charged particles moving, electrons are charged particles, and they move in wires when there's a current in that wire, and if charged particles are filled by magnetic fields, then current carrying wires must be influenced by magnetic fields. And you'd be right. So this mini lecture is going to look at how that all works. How does current carrying wires experience an external magnetic field? What happens? And you might suspect that it's a force. So let's look at what that is related to. So first of all, we know that current is dq dt. Right? The charge per time as it moves through a wire. And if we think about how fast that charge is moving, the rate at which it's physically moving, and the experience of charged particles knowing that how fast they're moving is related to the force. And this charged particle, the electrons are in a wire of some length, some dimension must be related to that force also. So the length, we might suspect, is related to the force that those charged particles feel, right? So because length is going to be a little bit related to its speed, how quickly can it get down to the end of that wire, for example, those charged particles. And when we put this together, when we look at the force that a magnetic field exerts on a wire, current carrying wire, that's going to be assumed in my description of wire, we find that it's related to the current times the length times the field times the sine of the angle. It's that cross product again, the sine of the angle of the wire relative to the field. Okay? So if I have a length of wire and I have a current in that wire, and I have a magnetic field, let's say it's going into the page that wire is traveling through. As that current goes through that area of the magnetic field, that wire is going to feel a force. It's going to bend, okay? We'll talk a little bit more about that later. But what I want, or move, bend or move, depending on if it's fixed or free to move. But let's take this wire and let's make it into a loop. Let's take the wire and make it into a square loop and see what happens to give this more perspective. So you have a magnetic field. So I'm going to put 2 ends of a magnet, north and south. We then know that there's a magnetic field between them. And that magnetic field is uniform. Okay, so I'm going to go with all that. Now I'm going to take my wire and I'm going to make it just into a square loop. And you have to forgive my drawing. Let's make it, because I want the wire to look in this, it's tilted within that magnetic field. So I've drawn the magnetic field in the plane of the board, and the wire's not in the plane of the board, okay? It's at an angle relative to the board. So I'm going to take a top-down view of that, all right? So the top-down view, so I'm just going to, as if I'm looking like this. Here, I'm going to try to use the same colors. Here, we're looking down on our magnetic field now, between these 2 magnets. And the wire is coming out of the page here and into the page here. So it's at an angle, right? And across the top, I'm going to see the wire across the top. Hopefully that makes sense. Out of the page and into the page. So what's going to happen to this wire? Well, if we imagine these 2 points, okay, the one that's going into the page, the current in that wire is going into the page here. Sorry, out of the page, it's a dot, out of the page, going across and then into the page. That's what's happening. So it's coming out of the page, perpendicular to that field. So like our cross product before, Our fingers are in the direction of the current. Our fingers curl in the direction of the field. So you put your fingers in the direction of the current out of the page. You curl in the direction of the field that way, and we see a force. We would see a force. I'm going to use pink. In this direction, we would see a force. This is the direction of the force. Conversely, as it goes into the page, we're going to, so out of the page, let me make sure I did that right. Out of the page, I curl in the direction, out of the page, curl in the direction of the force, of the field, field force. Conversely, this particle, this part of the loop, is going to feel a force in the downward direction. So what happens? I have that loop, this part of the loop feeling a force in the upward direction, this part of the loop feeling a force in the downward direction, and what does the loop do? It rotates. This causes a rotation. When I put my current carrying wire into a loop and put that loop into a magnetic field in a certain orientation, and we're going to explore that in just a little bit, the current carrying wire now rotates. If it rotates, think back to physics 1, that means it experiences a torque. So magnetic fields exert torques on current loops. A magnetic field can exert a torque on a current loop. All right? What's that torque going to be related to? So now we're going to look at magnetic current carrying wires and magnetic fields, but as loops. Think about what can that loop be a little bit related to. What is this, not the loop, the torque. What is the torque, the magnitude of that torque, how strong it can exert a rotation related to in terms of this current carrying loop of wire in a magnetic field. How can I get a bigger torque? Well, we know from our first exposure to torque that it related to the force, right? And the force that is causing the torque is a magnetic force, and we know that look at this information, that is related to the field. So if I increase the field, I should increase the torque. If I increase the current, because we know that the force is related to the current, I should increase the torque. Now, what if I have a number of loops? Loop after loop after loop. Well, that's sort of like lots of currents and lots of loops, lots of wires. If I increase the number of turns, I increase the torque. So N is the number of turns. The number of loops. And now this is a loop, and when we looked down on it, remember it has this sort of like length that we looked at the lengths. We looked at 2 of those lengths, and we're actually going to do an exercise where we look at all 4 sides, and that might help elucidate it a little bit more. But as we look at the lengths, we're actually looking at the whole cross-sectional area. That's what's going to become important. And so if we increase that cross-sectional area, we also increase the torque. Now, this leads to the torque relationship that we have for magnetic fields. The torque by a magnetic field is equal to the number of loops times the current times the area of that loop times the magnetic field times the sine of the angle. And this angle is between the magnetic field and the direction perpendicular to the area. We're going to give that a name in just a second. So it's the magnetic field and the area, but it's perpendicular to the plane that area makes. Okay? Okay, so you can imagine if I have a area that's a rectangle, okay, in the plane of this board, the angle that we care about between that and the magnetic field is going to be the area vector is perpendicular to this plane, okay? These three values together, the number of turns, the current, and the area, are what we call the magnetic moment mu, lowercase mu. So this is defined as the magnetic moment. And its direction, again, is perpendicular to the area plane, right? So this leads to the equation for torque in our vector format, because mu is a vector and b is a vector. And we get that the torque is equal to mu cross b. And again, whenever we have that cross product, we deal with the right-hand rule, and that angle is, of course, the direction, the angle between the direction of mu, which is perpendicular to the area, and the magnetic field. Right? So this relationship is important for us now. This relationship is that relationship. Okay? So mu is NIA. And then this relationship is what we're going to work with for a second. All right? So this is looking at how current loops are influenced by magnetic fields that causes rotation. And we're going to do an example in the next video. I want to break these up, and we're going to talk through that example about what happens when it rotates, when does it stop rotating, and how can we use all of that to our advantage. All right, so the examples in the next video. Good job.